Thank you everybody for joining us today for Protocol Labs Research Seminar Series. Today we're joined by PL's own Alfonso de la Rocha. Alfonso is a research engineer focused on distributed systems and advanced cryptography. Today he will be presenting his work titled Filecoin, Hierarchical Consensus Specification. Thank you so much for joining us today, Alfonso, and you can take it from here.
Thank you, Trent. First of all, today we're going to talk about a work in progress spec, so expect changes in the future. And I've been the chosen one to give this talk, but behind this work, there are a lot of people contributing. So we have great minds like Teris, George, and Marco. So thank you very much for all their contribution to this work. And what we want to present today is our hierarchical consensus, or our proposal to scale Filecoin and potentially other blockchains horizontally through this framework that we call hierarchical consensus. And to give you a bit of motivation of why we started working on this, it's widely known that one of the bottlenecks that current blockchains have is that transactions are validated sequentially because of how they're architected. We don't have an easy way of parallelizing the validation of transactions. Luckily, there are a lot of projects that are exploring how to do this. There are some projects that already have this validation in parallel in production, and we have examples big examples like the one from Ethereum, where they're exploring the use of sharding, for instance, in order to parallelize the validation of transactions. In our case, we think that a single consensus may not be the best way of, it can be a way, but it may not be the best way of scaling blockchains and accommodating any kind of use case. And that's why with hierarchical consensus, what we're looking is not only to scale horizontally a blockchain, but also a blockchain network, but also to be able to accommodate any kind of use case, and for the use case to be able to choose the consensus algorithm that better fits its needs. So if there is no one-size-fits-all consensus algorithm, let's accommodate any kind of consensus algorithm so that the application can choose what is the best option for them. And the idea is that with this framework, we should be able, or at least that's the target, we should be able to accommodate more crypto-native use cases like the case of DeFi, and more Web 2.0-ish applications where we have more load, higher throughput, and we have other kind of needs. And we know that there's usually a trade-off between scalability and security guarantees for these kind of protocols. So the idea is to let the use case choose what is the right balance for them. So that's why, we're giving them the framework to be able to spawn their own subnet for the use case so that they can choose this trade-off while still interoperate with the rest of the system. And that's what hierarchical consensus is a framework to enable this on-demand horizontal scalability. We are focusing Filecoin, but the idea is, if we can, to make it as general as possible in order to accommodate any kind of blockchain network. And it's you'll see here some properties from sharding, some properties from the sidechain approach, because it's an alternative approach where the idea is to support any kind of consensus and be able to horizontally scale blockchain networks. And really briefly and high level, what this framework, what we want to enable with this framework is to allow anyone to deploy their own subnet, or we could call it sidechain, but we call it subnet. You'll see in a moment why, ensuring the interoperability between the different chains in the network, building in this way a hierarchy of subnets. So we can have, for instance, I don't know if you can see my pointer. So let's think of a blockchain network like the Filecoin mainnet that we currently have, and we can optionally have another blockchain like Bitcoin, where we are periodically committing checkpoints in order to improve the security of this chain. This is another project that we have in Consensus Lab. And if you are interested in this work, you should definitely talk to Sarah. So the idea is that we have this root chain of the hierarchy, and we want to scale and spawn new subnets in order to parallelize the validation of transactions, and also to increase the throughput of the system. So the idea is that with hierarchical consensus, we should be able to spawn new subnets that are completely independent networks, that they keep their own state. So we're not partitioning the state. We are creating completely new state for anyone to use. And each of these subnets will run its own consensus algorithm. So the idea is to have subnets that run their own consensus algorithm, they run their own state, but that have the ability to leverage the security of their parent chains and the upper levels of the hierarchy, and at the same time interact seamlessly with any subnet that belongs to this hierarchy. And in this way, what we've done is that we are parallelizing the validation. We are accommodating other kind of consensus algorithms and also parallelizing the validation of transactions in the system. And something that I want to note early in the presentation is that in these subnets, what we try to enforce is, and what we want to enforce is a firewall requirement, which means that that is our main security assumption. Whatever happens in the subnet should have a limited impact in its parent and in the upper layers of the hierarchy. And at this point, what limited means in our current implementation is that the impact that an attack in the subnet can have over the parent is limited by the circulating supply that we have in the subnet. In the future, hopefully, we will have other kind of security requirements. But the reason why we have this requirement is because we don't guarantee any kind of security of guaranteed security in subnets. So we allow anyone to be able to spawn a subnet, start interacting with it, and we can't, like, for instance, enforce, or we don't want to enforce an honest majority in subnets. We want these to be as flexible as possible, but we ensure these firewall requirements. So if no one injects new funds into the subnet, we know that the impact that an attack over this subnet can have over the upper layers of the hierarchy will be limited by the circulating supply of the subnet. And finally, the way in which subnets can interact with the rest of the hierarchy is through what we call crossnet messages that I will introduce in a moment. And the same way that we can parallelize a root chain, we will be able to spawn new subnets that from a child subnet instead of from the root to go even deeper in the hierarchy and be able to scale further the system. And the way in which we implement this right now, so the two key pieces of this framework is first what we call the subnet coordinator actor, which is a system actor in the Filecoin lingua, or a built-in smart contract if you come from the Ethereum world. And this actor is spawned in every single subnet that wants to run hierarchical consensus, and is the gateway for hierarchical consensus, and it implements all of the logic for the framework. And then along with this subnet coordinator actor, what we have is a subnet interface that needs to be implemented by the subnet actor that governs the operation of new subnets. So if, for instance, we want to deploy a new subnet from this root chain, what we do first is to deploy a new subnet actor. This subnet actor implements the subnet interface that I'll show in a moment. And we can, once we have this, we can deploy the new subnet. But at this point, what we have is just a sidechain that we can start mining, that it has its own subnet coordinator actor, but that's it. We don't have a way of interacting with the hierarchy. In order for a subnet to be part of the hierarchy and be able to start like committing checkpoints to the parent chains, interacting with the rest of the subnets in the hierarchy and so on, subnets needs to be registered. So the way in which subnets can be registered to the hierarchy right now is that the founder members or miners in this subnet, they'll have to put some collateral in the subnet coordinator actor in order to register this subnet and be able to start interacting with the rest of the subnets in the system. And in the same way, like if we want to deploy a new subnet, we will first deploy the subnet actor that implements all of the policies, because like these subnet actors are configurable. So any user and any use case will be able to define the policies, but they have to implement the specific interface in order to interact with the subnet coordinator actor, and from there with the hierarchical consensus. But we're gonna go in depth into these functions and this interface in a moment. Like looking at more, looking to the system architecture a bit lower level, what a subnet is in the end is just an instantiation of all of the stack for a network from scratch. So it means like if we have different subnets, a new subnet, what it is just a new API that has its own chain, its own state tree. Of course, the VM implementations are shared because the applications throughout all of the hierarchy, messages need to be applied and state changes need to be applied in the same way. But each subnet runs its own consensus, it runs its own message pool, and it shares the transport layer in the sense that they're both libp2p, but each of them send their messages to a specific pub subtopic. And this is really interesting because it means that if we are able to discover the pub subtopic for a subnet, we are able to interact with that subnet and start sending messages to that specific subnet. And because of this is why the way in which we define the ID for subnets is deterministic, and it's quite straightforward. It's determined according to the parent of the subnet and the ID in the parent chain, that the ID of the actor that governs, that implements all of the policies and the subnet interface for that subnet. Which means that probably you've realized here that from the root, if we're deploying, we're spawning this new subnet, if the subnet actor that governs this subnet has an ID T01, it means that the ID for my new subnet will be root/T01. And this is really interesting because in that way, as the ID depends on the location of the subnet in the hierarchy, we have a way of discovering all of, and even traversing the hierarchy to find all of the subnets that we have in the hierarchy. In the same way, my second subnet will be root T12 because the ID of the subnet actor that implements the subnet interface for this subnet is T12. One of the requirements also for subnets in order to interact with hierarchical consensus is that they should sync with the state, and they should be listening to the state changes in the subnet actor and the subnet coordinator actor. Because as we'll see in a moment, a lot of, the parent is the gateway for the subnet to the rest of the hierarchy. So we'll see in a moment why this is also a requirement. So we the nodes in the subnet will be listening to state changes in the subnet actor and the subnet coordinator actor, because this is where a lot of the things related to what is happening in the hierarchy will be notified, and how these things are notified to the nodes in the subnet. As I was saying, we have two types of actor, the shard coordinator actor and the subnet interface and the subnet actor. In order to spawn new subnets, we have a deterministic way of identifying subnets, and we also have a way in which subnets can periodically commit proofs of the state of their subnet in their parent, so that they can leverage their security. So we'll see that we have a checkpointing protocol in which that is used in order to commit periodic proofs of the state of the subnet in the parent for the case in which there's an attack in the subnet, or for other kind of things that we are considering in the future. And I wanted to note it again, we don't assume guaranteed security in subnets. So subnets can do whatever they want. The only thing that we enforced in hierarchical consensus is the firewall requirements. So we want to limit the impact that an attack in the subnet can have in the parent and in the upper layers of the hierarchy. And if we look a bit deeper into the subnet coordinator actor, again, this is the unique system actor that is deployed in every network of hierarchical consensus. In this actor, what we see is this kind of functions. So we have a register subnet function that is called by subnet actors in order to put collateral and register their subnet in the hierarchy. We have the commit child checkpoint that is used to commit new checkpoints from subnet actor. These two functions can only be called by the specific subnet actor that governs the subnet. So it will only allow calls from actors that implement the subnet interface and the specific actors that with the ID that is performing the operation. Then we have a send function in order to send cross messages to other subnets and addresses in other subnets in the hierarchy. We have the apply cross message, which is a special function in order to apply messages that come from other parts in the hierarchy. Add and remove collateral. This, of course, has to be called also by the subnet actor. Kill subnet, and then a special function that I'm not going to go in depth because it's a bit under definition, that the idea behind this safe function is to have a way of, and probably we need FPM and a lot of things to come in order to implement it, but the idea is that it would be really cool if we are able to store either periodically or before a subnet is killed or so on, the state of a subnet, so that even when the subnet is no longer part of the hierarchy or no longer part of the system, we have a way of still accessing its state because it has been persisted either in Filecoin or somewhere else. And if we look a bit deeper into the state, the kind of things that we see in the SCA is some general information about like what is the name in the network, the total child subnets that it currently has, the minimum state required in order to register a subnet, information about the subnet, information about the checkpoint period, which are the number of epochs between checkpoints committed in the parent, as we'll see in a moment. We have like the committed checkpoints from childs, and we have like information about cross messages and the application and the routing of cross messages that, again, we'll see in a few slides. We had the subnet coordinator actor, and we also have the subnet actor, or actually the subnet interface, that here what any subnet actor that wants to be part of the hierarchical consensus, it needs to implement this interface with the policies that it wants to enforce for its subnet. So we have a constructor where we will have to provide some mandatory information, like for instance, what is the genesis, either how to generate the genesis or what is the genesis in order to start mining in that subnet, what is the consensus algorithm that that subnet runs. Then we have the join operation, which is the one used to provide collateral to the subnet and either add new collateral to the SCA for that subnet or register the subnet. We have a submit checkpoint, which is used to propose the submission of new checkpoints to the parent chain, and we'll go in depth into how the checkpointing protocol works, and then the kill and leave. All of these functions. So this is the interface, and each subnet may implement whatever policy they want over these functions. So it may enforce some kind of requirements, specific requirements in order to users to fulfill in order to join. The same for checkpointing. Each subnet may choose to use a different kind of verification in order to propose new checkpoints or even build different proofs in order to include in these checkpoints to the parent, and the same for kill and leave. We have our reference implementation of this subnet actor already, but the idea is for the subnet actor, once we have user-defined actors, to allow anyone to be able to determine their own, like implement their own logics over this. And if we look a bit deeper into the state again, like here, what we see in the subnet actor is information. Of course, this is the reference implementations. Anyone could implement the interface as they want, but like some information that we keep is information about the parent ID, the consensus that is run. We have a policy here that in order to become a miner in subnets, you need to add a minimum stake. All of these things could be stored in the subnet actor, the checkpointing period, which is also a mandatory argument for the constructor, where we define how often we propagate checkpoints to the parent chain. And with this, like with the subnet actor that governs the subnets, with the way in which we spawn new stacks in order to run the subnet, and with the subnet coordinator actor, we have all of the pieces that implement the operation of this hierarchical consensus framework. And with this, let me walk you through the life cycle of a subnet, now that we know the different parts that conform the hierarchical consensus. So if we want to deploy...
really quick?
Yep.
Do you mind if I interrupt you for a sec?
Yep.
All right. We have one question here in the chat from Nicholas saying, what consensus algorithm does the subnet runs? Means there needs to be a globally accepted list of consensus algorithms known by the whole network or only the parent subnet? Can you expand on that? So
we don't know yet. The idea is it would be great. I mean, we have to explore the possibilities, because right now as we don't have FVM, we are quite limited to the implementations that we provide. And at this point, like we provide a proof of work implementation. Of course, they are like testing environments, but we have a list of implementations of consensus algorithm. It's a really simple proof of work really dumb, what we call delegated consensus, where we choose a miner and it's more for debugging purposes. And now we are starting to integrate Tendermint. There will be more to come, like how high throughput consensus, hopefully in a few months and so on. But the midterm aspirational would be one where we allow anyone to come up with their own consensus algorithm, and it's kind of straightforward to plug in if they want. So we can have a catalog of consensus algorithm and have a way of allowing others to plug in their consensus algorithm, as long as they implement the interface of consensus that we will provide. But again, like, we don't know yet. Right now we have a catalog where you have to choose the one that you want to run in your subnet.
Great, thank you.
This is, I described briefly already this, which is, if we want to deploy a new subnet, what we do is we first deploy the subnet actor that implements the policies that will govern our subnet. We can start mining. What we have up to here is just a sidechain. And if we want to register this subnet, what we have to do is provide some collateral, either because some new founders join, or because like we provide all of the collateral and we wait for new members to join, but we are already registered. But the thing is that the subnet needs to provide collateral to the SCA. So there's a minimal threshold. Right now, like, for debugging purposes, we are trying to figure out the incentive system and like the cryptocurrency behind the framework yet, but right now there's a 2 Filecoin threshold that we use for debugging purposes. So the subnet needs to provide at least 2 Filecoins of collateral in order to be registered in the hierarchical consensus. And the idea of this collateral is that we have the firewall requirements, but it would be great if this collateral can also cover for potential losses in subnets. We haven't, again, figured out the right way to do this, or how will this collateral be dynamically adjusted and so on. But the idea is to have, like, first the firewall requirements and then a collateral that can be slashed and can be used to cover for potential losses in subnets. And the way in which we enforce the firewall requirement is through the SCA of the parent, because the SCA of the parent is the gateway for the subnet to the rest of the hierarchy. And this SCA keeps track of the circulating supply for the subnet. So as every cross message and every injection of funds and release of funds from the subnet is tracked, it has to go through the gateway, through the SCA, through the top level of the hierarchy. It means that the SCA can keep track of the circulating supply, and it can detect like weird minting of coins and so on. Like, it can detect certain attacks, and as long as they are over the circulating supply. If they're below the circulating supply, it can detect like double spend and this kind of attacks. And if we look like from the top, how spawning and joining a subnet would look like, what are the messages that we need to send to the right actors? First, like, the construction and the message to join a subnet is done in the parent of the subnet. So if we want to join or deploy a new subnet, what we interact is with the parent of the subnet. And then, like, according to if we are constructing or joining the subnet and we have enough collateral, the subnet actor will relay and add collateral or register according to what we're doing, either like joining and we are not registered, we need to register, or just adding collateral. It will relay this message to the subnet coordinator actor. So at this point, like, we have subnet running, and we have the subnet registered in the SCA of our parent. So it can interact with the hierarchical consensus, and we can start checkpointing, periodically checkpointing to our parent to commit proofs of the state of our subnets. As I've said, like, one of the required parameters in order to register in the SCA and to deploy a new subnet is the checkpointing period. So the number of epochs between checkpoints that will be committed in the parent chain. And these checkpoints are used for 2 reasons. Like, first, for this commitment of proofs of state, like, that anyone can implement as they want. Right now, we have a really naive approach where what we do is whenever we have a checkpoint window, we propagate up the tip set and at that epoch. So of course, it's not the best proof, but it's a way of, if we have access to the state, to be able to verify that the state is consistent. And along with this proof of the state of the subnet, we also include information about like the checkpoints. So we propagate up certain information about the checkpoint of that have been committed from childs. So here we add the CIDs of checkpoints that have been committed from childs previously, and then what we call the cross-message metadata, or I mean, we include information about the cross messages that need to be directed somewhere else in the hierarchy. So they're leaving our subnet and they're directed somewhere else in the subnet. So we're including like this proof that can be anything. Right now it's a really naive proof, but this can be anything in the checkpoint. And we have like information about cross messages. And the idea is that these proofs should be, I mean, it would be great if they can be proved in isolation. If not, like if they need to be, I mean, they should be verified by having access to the state. And this is one of the reasons why saving the state is also really interesting. And this cross-message metadata that we propagate is because instead of like propagating all of the messages that may be directed to a specific subnet and that needs to go through our parent, what we do is just propagate the CID of all of the messages to notify that there are cross messages that need to be applied in certain subnet. And we'll see in a moment how we resolve these messages, these cross messages, and they can be applied in the right subnet. And finally, like the subnets, once again, are free to choose their validation logic. And this is related to the question, because I like to think as checkpoints. I mean, I like to think of checkpoints as the clock of the system. So it's like kind of what runs and synchronizes all of the subnets in the hierarchy. And subnets are free to choose their checkpointing period. And how checkpointing works exactly and who does it is in the following way. We have two windows in the checkpointing protocol, what we call the checkpoint window and then the signing window. So in the checkpoint window is where we, like the SCA, starts collecting cross messages that needs to be propagated up to the hierarchy, and the new checkpoints that are being committed from its child subnets. So this is the checkpoint window in which we collect all of the data that will be propagated up. And I say that I like to call it the clock of the system, because when we have a flag in the clock, so when we reach the end of one checkpoint period, what we do is opening a new checkpoint period and opening as the signature window for the previous checkpoint. So in this, up to epoch 200, in this first checkpointing period, we were collecting messages and collecting like child checkpoint. This is done by the SCA, and then the SCA gets ready. It prepares a checkpoint template that needs to be populated and signed by miners in the subnet. So we have like these, we collect up to the end of the period of these messages and checkpoints. We have a new template, and we have like a new one more period in order for miners to build the proof that they want to propagate up to using the template that includes all of these messages and all of this information that needs to be propagated up. So miners get the template, they sign it, they commit it in the subnet actor in the parent, and the subnet actor runs the validations in order to see if it's a valid checkpoint, if it fulfills all of the corresponding validation, includes the proofs and includes all of the messages, and it relays this checkpoint for commitment into the SCA of the parent. So in the next checkpoint, so this is the signing checkpoint for epoch 200, and is the checkpointing window for epoch 300. We collect cross messages that need to be propagated for this period. We collect all of the child checkpoints in the same way. And once the period finishes, we have the signing window for the checkpoint of epoch 300, and we open the checkpoint window for epoch 400. And in this way, like miners in this way, we collect the template with all of the information that needs to be propagated up, and miners are the ones responsible. We could implement other kind of logic in the subnet interface, the subnet actor, but right now miners, in our reference implementation, miners need to sign these checkpoints, and we expect, in order to relay the checkpoint and consider it valid, the subnet actor waits for a majority of miners, so actually 2/3 of the miners, to sign the right checkpoint.
And I've got 2 questions here for you in the chat.
Okay.
One is, how do the miners sign the template?
So right now it's they sign with their private key, nothing like fancy. I know that, I mean, Sarah is exploring the use of DKG and other things for checkpointing. Eventually we may implement it here. At this point, we use the naive approach of having 2/3 of the miners sign it with their private keys. Okay.
And then the second one is, cross messages are aggregated per period. So that means cross messages latency is enforced by the checkpoint period, correct?
That's correct. Yes.
Okay.
So we have, and this, once we have like all the pieces in place, this is something that we want to explore, how we can like improve the throughput, because we are limited by the checkpointing period, that we don't know what is the best checkpointing period. And we are limited by the throughput of the consensus algorithm. So the block validation of consensus algorithm in the subnet and in the parent chain, which we don't know what that may be, or how to adjust the checkpointing period for the right consensus. So this is something to explore and make experiments around.
All right, thank you.
Yeah, and like looking at the messages that need to be sent to the right actors in order to propagate the checkpoint. With these raw checkpoints, miners get the template for the sign-in window, and what they do is they populate with the proof of the state, they include it in the checkpoint, they sign it, and once they sign it, they submit the checkpoint in the parent. I want to remind everyone that subnets always have to sync with their parent, and this is the kind of reason, because there are a lot of things that we do with the parent because it's our anchor of trust. So in this case, where we submit the checkpoint is in the subnet actor, and the subnet actor runs the policy that in our reference implementation checks the 2/3 of signatures. Someone else could come up with more fancy approaches, that hopefully someone will come with more fancy approaches for us to integrate. And once the fancy approach and the fancy policies is fulfilled, this is committed in the subnet coordinator actor. And the subnet coordinator actor, what it does is expect a checkpoint that needs to be initiated by the actual actor. So it only accepts checkpoints that come that comes from the right actor. So we can spawn subnets. We are committing periodically proofs of our state, and we can also leave and kill a subnet. This is done with the leave and the kill operations that we have in the subnet actor. The subnet actor will check or see if these leave and kill fulfill the policies that they are implementing, and accordingly, if they are fulfilled or not, they will relay the right release collateral or kill according to if we are leaving the subnet or we're killing the subnet to the SCA that will be responsible for releasing the collateral and giving it back to the right address. And if you recall from the registering stage, in order to register a new subnet, we need to have a minimum threshold of collateral. If we go below this threshold, so if enough miners or enough users leave and release their collaterals, and the collateral for the subnet goes below the threshold, the subnet gets in a frozen state. And what means to be in a frozen state is that no checkpoints can be committed and no cross messages can be sent to the rest of the hierarchy until the collateral is recovered. So until new joiners come and they add additional state. And with this, let's jump into crossnet messages. In the end, like a crossnet message is a message that is initiated in some subnet, and its destination is some other subnet. So it's not within the same subnet. And so the way in which we propagate crossnet messages changes according to what is the route that it is following, or the kind of message that we are sending. So we have 2 types of different crossnet messages, and then like complex messages that is a combination of these primitive messages. We have top-down messages. Top-down messages are messages that are sent to childs in the same branch of the hierarchy as the one that you can see here that goes from the root to one of its childs. The way in which we propagate these messages is directly by syncing with the parent. The fact that subnets need to listen to state changes in the subnet actor and in the SCA in the parent means that these crossnet messages that go down can be propagated like really straightforward by just listening to events and listening to the commitment of crossnet messages that are directed down in the hierarchy. And then we have bottom-up messages. These bottom-up messages go from a child to the upper layers, to the parent or to the upper layers of the hierarchy, or they go to some other branch so that it has to be a combination of both. These bottom-up messages are propagated through checkpoints. So these are the cross messages that we include in checkpoints. In checkpoints, we include the messages that need to go up in the hierarchy. And then we have what we call path messages that in the end is like any kind of routing, arbitrary routing through the subnets. And they're just a combination of a set of top-down and bottom-up messages according to what is their route through the hierarchy. So we have an example here. If we want to send one cross message from one of the childs to the other, what we have to do is do a bottom-up message. So we propagate the message with the checkpoint of this subnet first. And then once the checkpoint is committed, the SCA detects that there's a cross message that needs to go to one of its child, and it sends in a top-down message this message to the other child. And we call it path messages because they are arbitrary routed messages that are a combination of top-down and bottom-up messages. And in this way, we can route any cross message through the hierarchy. So we have the pipes in order to send these cross messages. If we look like, once again, what are the kind of messages in order to that orchestrate these cross messages, we have like, if we want to send a bottom-up message, so one message from this subnet to somewhere else, we need to send this message to the subnet coordinator actor where we want to initiate the cross-network message. So in this case, if we want to run a bottom-up transaction from a message from this subnet, we will call send cross to this SCA, to the SCA in the subnet. We will, and once the checkpoint is committed in the subnet coordinator actor, the message will be applied. I messed up this animation. This should have come afterwards. If we want a top-down message, it is quite straightforward because it's just like, if we want to send a message from the root to somewhere else, we just send this cross, send cross to the SCA in the parent or in the root. And these, like as the root, as the child is listening to events in the SCA, it will detect that there's a cross message that needs to be applied here.
I have one question for you from the chat here.
Yes.
What crossnet messages would be normally used for? There we go.
So right now, what we have implemented is Filecoin exchange, so token exchange. But the idea is that we could send any arbitrary message. So we could like have a miner living in one subnet and have the bookkeeping in the root and allow like to them to operate seamlessly. We could have like a subnet that is dedicated inside a data center that only members of the data center can join so that we can do really fast operations and then commit the state somewhere else. We're exploring the use cases. We have a lot of ideas, but not much bandwidth to test them. But the idea is that this would be a way of decoupling completely, like so we don't have user-defined actors right now in Filecoin, so we are in that sense quite limited. But once FVM comes, the idea is that we can parallelize and send arbitrary messages to subnets, and we can even have specialist subnets for execution. Yeah, we'll have to see. Hopefully, we will have a follow-up of this talk where we can introduce all of these cool use cases.
Wonderful. Going
a bit in depth on how these, because I told you that top-down messages is just listening to the state and applying the transaction, and bottom-up is just the checkpoint going up. If we go a bit lower into how this works, if we have a bunch of top-down transactions from a parent to a child, there is so we have two types of cross messages in hierarchical of message pools, sorry, in hierarchical consensus. We have the message pool that I showed that is dedicated for plain messages within the subnet. And then we have a special cross message pool, a special message pool that we could call the cross message pool that is listening for new cross messages that need to be applied in the subnet. The way in which like this cross-message pool listen to top-down transaction is that if the parent, like if in the parent there are top-down transactions that are directed to the subnet, as the child, the cross-message pool for the nodes in the subnet are listening to state changes in the SCA of the parent, they identify that there are unverified cross messages for the subnet. And the way in which we identify these unverified messages is that every new top-down message is assigned for this specific subnet, is assigned a unique nonce that is used for ordering and in order to identify what messages have been already applied. So when we see that there are new nonces, new top-down transactions that need to be applied, the cross-message pool takes these messages and includes them and proposes them in a block for the subnet consensus as if it was any other plain message. So cross messages are sealed and validated in a block the same way that any other message will be validated. So the child consensus algorithm will, so the cross message pool will propose these cross messages. The child consensus algorithm will commit, like seal the block, validate the block, and then when the block is committed, these cross messages and the state changes that need to be triggered through these state messages are executed as any other message in the subnet will be executed. And this is how we apply top-down messages. We listen for new top-down messages and we apply them in the subnet. And for bottom-up is similar, but not quite, because we can have a bunch of bottom-up transactions that are initiated in the child chain or that have been propagated from somewhere below the hierarchy and that needs to go up. And what we propagate in the checkpoint is not, as I mentioned, is not the messages, the individual messages, but in order to avoid a state explosion, we just send the CID of the cross message meta that we call, which is just the CID of all of the information, all of the messages that need to be propagated up and applied up in upper layers of the hierarchy. So we propagate this information with the checkpoint, and the cross message pool, what it does is that, so the SCA, once the checkpoint is committed, it detects that there are pending messages that need to be applied in this subnet, and the cross message pool, the same way that it listened to bottom-up messages from its parent, it also listened, for top-down messages from its parent, it also listened for bottom-up messages in its own SCA. And when it checks that there are cross-message meta with an increased nonce that hasn't been verified, the cross-message pool gets this message meta and resolves the messages behind the CID. So what it will do is, through the content resolution protocol that I will describe in a moment, it takes all of the cross messages directed to this subnet behind the CID that was propagated in the checkpoint. And with this, we have the list of messages that need to be applied, and we do the same that we did with top-down messages. We include the messages, we propose the messages in a new block, we commit the block, and then we apply with the messages, with the rest of the messages, the cross messages that were propagated to the subnet with the bottom-up approach. And I told you that there's a cross-message resolution protocol, and this is used to learn what is behind the CID of the cross-message metadata that is propagated in checkpoints. And the way in which we do this is the following. What we do is that whenever a new checkpoint is signed and propagated up, we also push the messages behind the CID to the pub subtopics of the corresponding subnets for the case that they want to pick it up and resolve it locally once the checkpoint arrives. This protocol have three main messages: a push message and a pull message and a response. The push message is for this, when we sign the checkpoint, we push it for the case that someone wants to store it locally and resolve it locally once the checkpoint arrives, so that we save time. And the pull is for the case where we may receive a checkpoint. We haven't seen the pull request, or we're syncing from scratch, so we don't have that information because we weren't listening in the topic then. And we pick up, so we pull the messages that are behind the CID. In the same way, once the messages are propagated up, in order to apply them and know what is behind the that CID with, this subnet will worry about pushing it to the right subnet. But if it is the case that when we need this CID, we don't have it, the content resolution and the state manager, what it will do is say, hey, before we can apply this message, have this message in the cross message pool, we need to pick up what messages are behind this CID. And this is recursive, so it may be the case that you need to go here and you see another CID that aggregates messages that are deeper into the hierarchy, and the content resolution protocol handles all of this recursive resolution of messages. And I'm not gonna present this because first, I'm running out of time, and second, it's under definition, but I just wanted to give you a glimpse of something that hopefully will come soon, which is atomic execution in common subnets. So here we are only like sending messages that will trigger state changes in the destination subnet, but it may be the case where we have two parties, like for an NFT exchange, that's a basic example. We have two parties in different subnets that they wanna perform an execution with state that lives and is held in their own subnet. In this case, what we are figuring out is a way of doing an atomic execution in a common subnet, so that we can migrate the state to a common subnet that we both trust. The obvious one is our parent, because we both have trust in our parents and we're syncing with them, and have a way of doing an atomic execution with state that live in different subnets and state that we hold in the different subnets. And again, like this is on the definition. We could share what we're thinking, but like I'm running out of time and we haven't fleshed this out, we're gonna leave it to some other talk. And so I'm gonna show these. I'm gonna show the life cycle of a subnet. So I'm gonna spawn a new subnet, see how it mines and so on, and then I'm gonna show how. I'm gonna do some Filecoin exchanges between different subnets. Of course, I'm not gonna use this complex hierarchy because it would mean like spawning a lot of subnets, but I will spawn a few. And what we're gonna see is that how messages get aggregated and propagated up in checkpoints as they go up, and then applied through top-down messages. And we hopefully will see how like as we go up, as we send transactions and we go up, the circulating supply and the balances of the different users involved in the transactions gets updated as the message flows. If it works, we'll see. And before I leave the slides, if you want to keep up to date to what we're doing, you of course have like general info in the repo of Consensus Lab. You have the Eudico repo, which is a fork of Lotus, where we are implementing all of these cool projects, and like you can like run it and start spawning your own subnets, because we have hierarchical consensus. We also are integrating interdomain. Like all the work of Consensus Lab is done over this base code. So if you want to keep up to date to what we're doing, definitely go to this repo. And then we have the living spec, where hopefully soon you'll see these things around the atomic exchange, and you can read like all that I've presented in these slides. And also in this general info, or somewhere in the repo, you'll have access to these slides that I've used today. Okay, so here what I have is already two Eudico nodes started and connected, and I'm gonna start mining in what it would be our root chain. So you see that right now we have like two nodes that are mining the root chain, and we only have a root chain at this point. What the first thing that we're gonna do is we're gonna add a new subnet. Here what we're doing, but we're adding a new subnet with a human readable name and running the consensus #1. This is what I meant that we have a catalog. The #1 is a proof of work. So I'm gonna start a new subnet that runs proof of work. This, what it does is just deploying the subnet actor. So you see the subnet actor has been deployed in this address, and the new subnet is available with this ID. If we list the subnets from the root, we see that there are no subnets. And the reason for this is that we haven't registered the subnet yet, because we haven't provided the right collateral. So what we're gonna do now is to join the subnet from this peer with the right ID. and we want to provide 2 Filecoins of collateral, which is the minimum in order to register the subnet. And now, like when the message is sent, we've successfully added state to this subnet. And if we list the subnets, you see that we have now one subnet that comes from the root that is active because it has the minimum stake, but it has a zero Filecoin of circulating supply. At this point, like we are doing nothing, so we are not mining in the chain, but we could start mining the chain here. And what we're gonna see if we go to the logs is that, so you see that here we even if we are not mining the root chain, now we're mining in 2 chains in parallel. And as this guy is the only one, so this node is the only one that joined the subnet, this doesn't see any of the new blocks that are being mined in the subnet because it's just syncing with the root chain. If we join from the other, so instead of providing collateral, we can start syncing with the subnet without providing additional collateral because we don't want to mine and we want only to sync with the subnet. Wait, again, I messed up the. What we're gonna see now in the logs is that actually we are syncing with the subnet. So we now have a root chain and a subnet mining in parallel. I'm gonna start mining back in the. So now we're mining in 2 subnets at the same time. So we have 2 nodes. We have a subnet. What we're not going to do now is inject some funds into this subnet. So we have this fund operation where if we look where we can send to our own address some additional funds to the subnet. And we'll see in a moment that so right now we are not, if we see our wallet and our balance in the root chain, which is 145 because I'm the miner and I'm receiving a lot of rewards, it's not the same as the one that I have. Sorry. In the subnet. So we have 2 different chains with the 2 different state trees. And if we look at the list subnets, we see that the circulating supply has gone up. What else we can do? So actually, the next thing that we're gonna do is so here we are listing the checkpoints that are being propagated from this subnet to the parent chain, which is the root. And what we're gonna do is see how a message, so we saw a top-down message, which is I'm injecting funds to my own in the subnet. What we're gonna see now is how I release funds from the subnet, and we should see a bottom-up message that is propagated through the checkpoint. And the circulating supply should be reduced. So if we now release 0.5 Filecoins, in the next checkpoint, what we should see is a cross message is true because it means that it has cross messages that needs to be propagated up. Okay, it's proof of work, so I should have chosen a faster consensus maybe. We see that here, like in the next checkpoint, the cross messages, it includes cross messages. So when the checkpoint is committed in the SCA is gonna take this cross message and apply it. So if we go to list subnet, we should see now that the circulating supply has been reduced and we've successfully released from the subnet some funds. And now what we're gonna do, finally, is we're gonna add a new subnet, and we're gonna do what we call the path message, which is the message that goes that it has a bottom up and a top down. So let's join 01. So we're joining a new subnet. We're going to start mining in the same way in the new subnet. Now we're mining 3 networks at the same time and in parallel. And what we're going to do is send some. So if we see in the wallet, so here in the first subnet, I have 1.5 Filecoins. In the new subnet, I should have 0. in the new subnet, I have 0. And what we're going to do is try and send a cross message that goes from this subnet, which is the root T01, to the other child of the root. And these can be done like this. We're going to send 0.2, for instance, from the first subnet, which is T0100, to the one that ends on 01. And wait, instead of, yeah, and I'm going to send it to, this is another completely different address that is not myself, to show you that you can send any kind of arbitrary message and not like messages to yourself. So here we should start seeing in the next checkpoint, we should see that the cross messages is in true, because we have a bottom-up message going up in the hierarchy, and then we should have a top-down, if I did it right. Yes, we should see, yay, a true here. So we are propagating the message up. The circulating supply should be updated. Yes, 1.3. And now we should have a top-down message where we should see here the 0.2. Wait, it's not in this one. I need to import the new key because I sent it to some other address to show you that it worked. Wait, it's this one. And yay, we have, like, we sent across-net messages between two different childs. And finally, like, we could kill one of the subnets. Let's kill actually this one so that we stop seeing checkpoints being propagated. We're gonna leave the subnet, and when we leave the subnet, you'll see that we won't be able to see checkpoints anymore. And if we look the list of subnets, you'll see that as we, so the status is inactive or frozen because we don't have enough stake in order to interact with the rest of the network. So we won't be able to interact with the rest of the network. And we have circulating supply, which means that someone will have to put collateral if they want to get their Filecoin back. And yeah, and like we could also kill, not the session, which could also like kill and unregister, like killing just unregisters the subnet. Okay, I don't know why is this failing, but we could kill the subnet. Maybe I'm doing something wrong. But we could kill the subnet, and then in list subnets, we shouldn't see, like, it would unregister completely the subnet. And I guess actually, like, you can, all of this is inside the Vico subnet. So if you want to check out, like, if you want to play with more of the commands that we have available, feel free to do so. I haven't shown all of them, just a bit of life cycle. So feel free to have a look at them and play with these. And if you see bugs, please, I'm the only one using these, so please notify them. And that's it from my side.
All right. Thank you, Alfonso. Thank you so much for coming, everybody. We're going to close it out. As always, to stay up to date with new talks, feel free to give our Twitter account a follow @ProtoResearch. You can also sign up for our newsletter. That's going to be down in the video description. And thank you so much for coming. We look forward to seeing you again. And Alfonso, thank you for presenting your work today. It was a great presentation, and we look forward to seeing how it continues to evolve in the future. So thank you again.
Thank you, everyone. Thanks.